Hello everybody. In this final video about acids and bases, I want to introduce a couple of important concepts and a little bit of new language and talk about acid-base ionization reactions. So an acid ionization reaction is one that produces a hydronium ion from water. And this is really kind of important for a couple of reasons. So far, I have written out acids as producing free protons, but in fact, that's not really true. What winds up happening is that free proton will wind up associating with a water and producing something called a hydronium ion, which is H3O with a +1 charge. And new theory in acids actually suggests that this may not even be true, that it's not really associated with just a single water molecule, but several. And that's why these protons are stable in water solutions. The math will always work out the same no matter how you write it out, but this is a little bit more correct way of writing this. The other thing that's important to note is that pH really only has any meaning when we have water as the solvent, right? Because it's based on the kW. If we don't have water, then it is not, we can't really talk about pH and pOH or any of that. So it's important to know how it's going to react with water. And here we have an example where we have pH 4. Within a +1 state, it gives a proton to water, and we get pH 3 plus our hydronium ion. Base ionization reactions are those that produce hydroxide ions from water. So here we have a Bronsted base, S2-. It's going to grab a proton from water. It's going to produce this conjugate acid here and a hydroxide ion. And it's important for us to remember that all acid-base reactions are actually equilibrium reactions, and we only even made an approximation when we were talking about Arrhenius reactions, where we said that they lied all the way to the right. In fact, there's always some kind of equilibrium, even if it lies really heavily to one side or the other. The acid-base ionization reactions allow us to give us the language and the nomenclature that we need to talk about the ionization constants for an acid. So if I have some generic acid here, HA, it reacts with water. It produces a conjugate base plus a hydronium ion. I can write out an equilibrium constant for it. I'm going to indicate that it's for an acid by putting a little a there. And I write it out here with our products over our reactants. Remember that we're going to omit pure water because it's a pure liquid. And we get our Ka. This is now a measure of how strong this acid is, how much it's going to dissociate and move to this side. So this is a quantitative value that allows us to figure out how strong our acid is. And we can do the exact same thing that we've been doing and talk about the pKa of this by taking the negative log of the Ka. If I have some generic base that's able to accept a proton, I can write out the Kb for it, where I have the products over the initial B- concentration. And I can talk about the pKb of this as the negative log of the Kb. So as the acid strength increases, the Ka of that acid is going to go up. This is a value we can look up. The pH of the solution is going to go down, and the pKa is going to go down. As the strength of a base goes up, its Kb is going to go up, the pH is also going to go up, and the pKb is going to go down. Notice that these have inverse relationships because of the negative sign that we have right here. one of the interesting things that we can do with KAs and KBs is take a look at the special case of a conjugate pairs. So a acid and its conjugate base. So if I write the equation like this, I have a generic acid, I get this Ka. But if I reverse that reaction, I now have a base that's reacting with water, and it's going to go back and form this hydroxide ion. And now I can write the Kb for the conjugate base of this acid. And I will get HA over HO minus over A minus. If I multiply the Ka by that Kb, I will substitute those in here, I get this. And I can see now that this is going to cancel with this guy, and this guy's going to cancel with this guy. What I wind up with is the concentration of hydronium ions times the concentration of hydroxide ions, which we know is equal to Kw. Remember that hydronium ions can stand in for those free protons. It's just a different way of writing the exact same idea. And we draw this conclusion that Kw is equal to Ka times Kb. So as the strength of the acid goes up, Ka goes down. But to maintain this relationship here, that means that Kb has to be lower. So our conjugate base is less, the stronger the acid is, the weaker the conjugate base is going to be, and vice versa. This is how we get this inverse relationship here. And we can do the exact same thing that we did for pH and POH and say that the pKw is equal to the pKa plus the pKb.